Let's do some work today. Work is related to energy in the sense that it's defined as the change in energy experienced by an object, the gain or the loss of energy experienced by an object. Now, in order for energy to be gained or lost by an object, two requirements have to be met. What do you got to do to change the energy of an object? What do you got to do work on an object? Let's take a look at this desk up here in the front. Right now, this desk has zero energy. If I want this desk to gain energy, what do I got to do to it? I got to push it. I got to apply a force. That's right. I got to apply a force. So one of the requirements for work to be done is to apply a force. But that's not enough. Right now, I'm applying a force, albeit a small force, still a force. I'm not doing any work on this desk. You know how I know I'm not doing any work on this desk? Because it isn't changing speed. It's not increasing energy. So how is it that I apply a force on this and actually change the energy of this desk? What else has to happen? It's got to move. You've got to have a displacement. If you don't have a force, you're not going to increase or decrease the energy of something. And if that force isn't applied over a certain displacement, then you're also not going to increase or decrease the energy of something. So you need a force and you need a displacement. Now, it's important to note here as well that this force and displacement need to be parallel to one another. It's not enough just to have a force. It's not enough just to have a displacement. It's not enough to have a force and a displacement. We need to have a force that is parallel to the displacement. In other words, we need to have a force that is affecting the motion. If I have a curling rock sliding down the ice, and I apply a small force on it downwards, I'm not going to affect the motion of that curling rock. If I apply a force on it horizontally, I'm going to cause that curling rock to either speed up or slow down. In other words, to change its energy. So if I apply a force parallel to its motion, I change its energy. If I apply a force perpendicular to its motion, I don't change its energy. The curling rock just keeps going as if it was not having a force applied on it. So the force needs to be parallel. The force needs to be parallel to the displacement. Now, here's the good news. The equation that we're going to use to describe the work accounts for that already. It allows us to get, if we don't have a force that's parallel to the displacement, it allows us to get a component of the force that is parallel to the displacement. Remember those wagon problems? You're pulling a wagon at 30 degrees or 40 degrees and the wagon moved horizontally? We could find the x component of that force, and that would be the force that we need. But the equation does that for me. So let's write down the equation. Work is equal to, well, let's write down the definition of work first. Work is equal to delta E. Work is equal to the change in energy. This is the Work-Energy Theorem. Work is equal to delta E. Which, by the way, delta E is final minus initial energy. Now, work is also equal to, well, it depends upon force and displacement, so it's force times displacement. But I'm going to tack a cos theta on the end of this, so that the force and displacement, if they're not parallel to each other, we make them parallel to each other by finding the x component of the force, which would be the same direction as the displacement. We're going to say work is measured in joules. Work is a scalar, because it's just a change in energy. This is the change in energy. That's also measured in joules, and that's also a scalar. F is force, and this is going to be measured in newtons. Force is a vector. Displacement, that's going to be measured in meters, and that's also a vector. When you multiply a vector by a vector, you get a scalar. So force times displacement giving me work is vector times a vector getting a scalar. Now what's theta stand for? Angle, right? But we got to be specific. It's not just any angle. It's the angle between the force and the displacement. The angle between the force and the displacement. If the force is to the right and the displacement is to the right, what's the angle? force and displacement are both this way, what's the angle between the two of them? 0. If the force is this way and the displacement is this way, what's the angle between them? 90 degrees, right? If we tack on the cos theta on the end of it and use the angle between the force and the displacement, then that's going to give us the x component of the force, which gives us the force that's parallel to the displacement. Let me give you a couple scenarios here of different forces and displacements in directions and see if you can interpret them, okay? So let's say again, let's just draw out the example we just gave you. We're pushing it this way. We're pushing it this way, and the displacement is this way. It moves this way. What's the angle? Theta would be what in this case? 0. 0 degrees. Now, just out of curiosity, does anybody know what cosine 0 is? Cosine 0 is? No? Try it. Yeah, it's just 1. Cosine 0 is 1. So, cosine 0 is equal to 1. So if we actually write the equation for work, W is equal to F times D times cosine theta, and if we substitute in 1 for cosine theta, because the angle is 0 degrees, then it just becomes F times D. In this scenario, work is equal to F times D because the object moves parallel to the force. If you want to keep the cos theta on the end of it, that's fine. But if they move in the same direction as the force is, then you can drop the cos theta if you want, because it's always going to end up being just F times D. How about this one? Let's say that it moves this way again, but it's like that wagon problem where we have a force this way at an angle of 40 degrees. What's theta in this case? 40 degrees. So this time we have to use W is equal to F times D times cos theta, because the cos theta is necessary to make F parallel to displacement. Really what we're doing here when we're finding cos theta is finding the x component of the force. We just don't have to do it separately because the equation doesn't form it. Now what about this one? What about this one? It's moving this way because of whatever. I apply a force this way on it. What's the angle here? What is it? Okay, I thought you were ready to speak there, but no? Okay. You get the right answer anyways. Even if you weren't ready to give me an answer, you still got the right answer. 90 degrees. What's cosine 90? 0. Now, if we say F times D times cosine 0, or cosine 90, I should say, then the equation just becomes 0. F times D times 0 becomes 0. There is no work done in that case, right? Why? Well, because the force can't possibly be parallel to the displacement when it's perpendicular to the displacement. None of it is parallel to the displacement when it's perpendicular. How about this one? How about this one? Let's say we got an angle of 30 degrees. That's what we seem to like to do here. We've got an object on an incline right here. We're pulling it like this. Of course, it's moving up the hill. What's the angle in this case? 30 degrees? 30 degrees? What is it? It's 0 degrees. Just because we have an angle given to us in the problem doesn't mean it's the angle that we use. The angle that we use has always got to be the angle between the way that it moves and the way that it's pushed. It's pulled up the hill here, and it goes up the hill. So the angle would be 0 degrees. So we'd say work is equal to F times D times cosine theta, which is 0 degrees. But because cosine 0 is 1, the equation just becomes F times D. Whenever the object moves in the same direction as the force, we can simplify the equation, if we wish, to just say F times D. What about this one? Here's another one that's... I'm confident you guys are going to get this, but here's our object. It's moving up the hill like this, but we're applying a force like this. It's 70 degrees. What theta do we use here now? 70? We're not pulling it in the way that it's moving, right? 70 degrees? What does theta stand for? Like not just any random theta, but what does the theta in that equation stand for? Parker?
Is the angle measured is the baseline perpendicular to the thing?
I don't know what, I'm not sure what you're saying.
Like, is the angle
Is this one right here? That's definitely not perpendicular to the inclined plane. That's parallel to the ground. Like parallel to this one down here. So what's my theta? No, it's not 70. What is it? What is it? It's 40. The angle that we use here is 40 degrees. We'd say work is equal to F times D times cosine 40 degrees. Why do we use 40 degrees? It's not just any random angle we want. It's the angle between the way that it moves. It moves at 30. And the way that it's pulled. It's pulled at 70. So the angle between the way that it moves and the way that it's pulled is 40 degrees. Does that make sense? Honestly, I doubt you see a question like this. Okay, a question like this, absolutely. Absolutely, that's fair game. But that one's easier because we just say F times D. Question like any of these, absolutely we could see. We could do something like this, just a little bit harder, that's all. Yep. Yep. Let's take a look at an example. Example number 11. A force of 200 newtons is applied to the right on a 20 kilogram box. While the force is being applied, the box moves to the right 300 meters. Calculate the work done on the box to determine the change in energy of the box as well. Let's write down some givens here. We're applying a force of 200 newtons, and we're applying that force, that's not work, that's force. That force is to the right. My displacement is also to the right. What's the angle between the way that it moves and the way that the force is applied? 0. I'm going to say theta is equal to 0 degrees here. Now, the mass of this box is 20 kilograms, and we're trying to determine the work done on the box, and we're trying to determine the change in energy. We'll worry about the second part after we finish the first part. The equation that I would typically use here is W is equal to F times D times cosine theta. But since theta is 0 degrees, cos theta becomes what? Cos 0 is 1, which means if I want, I can just drop the cos theta right off the top. You can put it in if you want, and then just write in F times D times cosine 0 degrees and see that it's 1, or you can just drop the cos theta. If it's parallel, force is parallel to the displacement, you can do this. Force is 200 newtons. The displacement here is 30.0 meters. We multiply those together, we get 6 with 3 zeros. 6,000 joules, which we're going to round to, how many digits would this be? This one is 3, this one is 2, this one is 3. Final answer should be 3. Why is the final answer 3 here? Why is our final answer 3? We didn't use that 20 kilograms, right? We didn't use it, so our answer is 6.00 times 10 to the 3 joules. Now, what's the change in energy of the box? Same thing. Work is equal to the change in energy. So if work is equal to the change in energy, then my change in energy is 6.00 times 10 to the 3 joules as well. Example number 2 says a 15 kilogram wagon is being pulled to the right with a force of 100 newtons at 30 degrees above the horizontal. So let's assume that it moves to the right, but it's being pulled at 30 degrees above the horizontal to the right. Let's write down some givens here. Mass is 15 kilograms. We got a force here of 100 newtons. And I got an angle here, theta, of 30 degrees. The displacement is 300 meters. And we want to find the work done on the box. This time when we write down our equation, W is equal to F times D times cosine theta, we can't drop the theta, the cos theta this time. Now remember, we're not just putting in a random angle. We're not putting in 30 because 30 is in the question. We're putting in 30 because that is the angle between the force and the displacement. It's the proper angle. F is 100 newtons. Displacement is 300 meters. And theta is 30 degrees. So we're going to say here it's 100 times 300 times cosine 30 degrees. It should give you a value of 25980. 0.762 joules, which we're going to round to, if we look at our data here, this is 2, but it doesn't count because we didn't use it. This is 3, this is 2, this is 3. Final answer should be, yeah, it should be 2 digits this time. 2.6 times 10 to the 1, 2, 3, 4. 2.6 times 10 to the 4 joules. We're not asked for the change in energy of this one, but we could find it, right? The change in energy is 2.6 times 10 to the 4 joules. Same thing. We can have a look at worksheet number 18 now, your worksheet. There's 6 questions on that sheet. I would like you to do worksheet number 18 for now, at least. Only questions 1 to 3. Worksheet number 18, let's take a look at questions 1, 2, and 3 now. Number 1 says, a 2-kilogram toy is pushed with a force of 10 newtons at 60 degrees above the horizontal over 4.5 meters. How much work is done? We're going to say work is equal to F times D times cos theta. We have to include the cos theta here because there is a theta. My force is 10 newtons. My displacement is 4.5 meters. And my angle is cosine, or my angle is 60 degrees. So I'm going to say 10 times 4.5 times cosine 60. 10 times 4.5 is 45, times a half is 22.5. And I'm going to round that to 2 digits, which is 23 joules. So the work done is 23 joules. What's the change in energy? It's the same question, right? It's the exact same question. The change in energy is equal to the work, so we're going to say the change in energy is also 23 joules. What type of energy did the toy have just before it was pushed? It's a trick question. It had none. There was 0 energy just before it was pushed. So how did it get pushed forward? Well, there had to be energy that went into it to push it forward, but it wasn't energy in the toy that pushed it forward. It was energy in me. Chemical potential energy stored in me, or whoever it was that pushed it forward. That chemical potential energy was transferred to the box or to the toy and became kinetic energy as the car went forward. What type of energy does the toy have after it was pushed? We just said that it was kinetic energy. So potential energy is converted to kinetic, but the toy didn't have potential initially. It was whoever pushed it that had potential initially, and that got converted to kinetic in the toy. 2, 1,000 kilograms of work is done on a 5-kilogram object and moving at 12 meters. How much net force must be applied to accomplish this? Let's assume, if it doesn't say otherwise, that it moves in the direction it's pushed. Therefore, we can, if we want to, drop the cos theta. If we want to keep the cos theta, that's fine, but theta becomes 0 and cos theta becomes 1, so it's the same thing as just dropping it. We're looking for the force here, so let's say F is equal to W over the displacement. The work is 1,000 joules, and the displacement is 12 meters. And that's going to give me 80, what is it, 83.3? And that should be 3 digits. Again, the 5 kilograms doesn't count because we didn't use that. 83.3 newtons. What's the answer? Quick, lightning fast, number 3. 83.3 newtons. It's the same question. The point that I want to make with questions with this information right here, 1,000 kilograms, 1,000 joules of work, 1,000 joules of energy is gained. And similarly, the point that I want to make up here where we said, what's the box's work done? The work done on the box, and what's the box's change in energy? The point that I want to make is that you could get a question on a test that asks you for the work done. You could get a question on a test that asks you for the change in energy. You probably won't get both, but you need to recognize that you do exactly the same thing to get change in energy as you do to get work. It's the exact same question. Okay, let's do one more example on this stuff here. Let's have a look at example number 13 now. It says the driver of a 1,200 kilogram car was traveling at 25 when she slammed on the brakes and came to a stop. So this time we're not speeding up, we're slowing down, but that's still a change in energy, right? And if there's a change in energy, there's work done, because that's how we define work, as a change in energy. If the magnitude of the force of friction acting between the tires and the road was 9,000 newtons, that's what stops the car, right, is friction. So the force applied is 9,000 newtons. How much energy did friction take away from the car? How much work did friction do on the car? And how far did the car skid? So picture this. The car's moving to the right. Friction's going to slow this car down, which means friction's going to act to the left. Are they parallel? Yes, they are. Do we have to include cos theta? No, we don't. Because they're parallel, we don't need to include cos theta. Technically, the angle wouldn't be 0, it would be 180 there, but cosine 180 is just -1, which gives us a negative work, which means it's energy lost. So in the end, we can still drop the cos theta if we wish. All right, let's find the energy that was taken away here. So let's find delta E here, delta E. I don't know what D is. I don't know what the distance is or the displacement. So here's what I'm going to do. I'm going to say delta E is EF minus EI. And I'm going to say that's equal to, well, what kind of energy does this car have at the end of the problem once it's stopped? None. Final energy is 0. What's the initial energy when it's moving at 25 meters per second? What kind does it have now? Yep. Kinetic energy. So we're going to say it's 0 minus 1/2 mvi squared. Change in energy, or the energy that friction took away, is 0 minus 1/2 mv squared. So that gives me 0 minus, or just negative 1/2 of 1200 times 25 squared. When I do that math on my calculator, I get negative 375,000 joules, or negative, I'm going to round that to 2 digits, negative 3.8 times 10 to the 5 joules. Can you tell me why that's a negative value? Didn't we say that work is a scalar and therefore has no direction associated with it? How do we get a negative if work is a scalar? Yes. Okay, it doesn't mean that it's in the opposite direction. It doesn't mean that the work is to the left or to the south. It means that we're slowing down and therefore have a loss of energy. Negative work or negative change in energy is a loss of energy, whereas a positive work or a positive change in energy is a gain of energy. Parker?
How much energy did friction take away from the car? Friction took away negative.
Yeah, no, I see what you're saying there. That's a good point. By rights, when we answer question A, how much energy did friction take away, we should take the absolute value of that and just say 3.8 times 10 to the 5. The change in energy, which is actually what we solved for, it's not what was asked. Okay, we asked for how much it took away. We solved for the change in energy. That is negative because it was a loss of energy. But if you, strictly speaking, to answer this question perfectly correct, we should drop the negative because we should make it an absolute value. I'm certainly not going to take off a mark if you don't do that, though. Either way in this case. Okay? In the end, we've solved for delta E correct. It should be negative 3.8, but the loss of energy should be the absolute value of that, if that makes sense. If it doesn't, don't panic about it because I'll take either one. All right, how much work did friction do on the car? I didn't leave very much space to do this. How come? It's the same thing. Yeah, the work is equal to negative 3.8 times 10 to the 5 joules. Now, there is another way to do this. We could have said A is equal to F over M, solve for the acceleration. And then we could have said, let's see here. No, sorry. We could have said VF squared is equal to VI squared. No, that wouldn't have worked. Yeah, we could have solved for the acceleration using A is equal to F over M. And then we could have said VF squared is equal to VI squared plus 2AD to solve for the displacement. And then we could have said F times displacement gives me the work. Okay, that would have worked. Okay, I just think that this is a more efficient way to do that question, that's all. Having said that, if I had done it the other way, I would already have the answer to C. I don't, so let's go back and say work is equal to F times D. Force and displacement are in the same direction, so I can do this. We're going to rearrange this, solve for D. I get work over F. The work, use the unrounded number, negative 375,000 joules divided by the force of 9,000 newtons. We do that, we should get a negative value. And it is 41.7, negative 42. No, hold on. Oh, wait a second. What have I done wrong here? Yeah, that should be a negative value for work, right? But friction should be a negative value as well, right? Because friction acts to oppose the motion. So when I divide those two, I get positive 42 meters. Let's take a look at worksheet number 18 again, but let's this time focus on questions 4, 5, and 6 on that worksheet. Let's have a look at question number 6, guys. Some of you are finished it, some of you are not, but that's okay. Let's plug forward with it anyways. 6 says a 0.43 kilogram ball traveling at 130 kilometers per hour hits a wall and comes to a rapid stop, squishing itself 2.3 centimeters. We want to find the force of the wall acting on the ball in order to stop it, and the force of the ball acting on the wall. Let's circle these because we want to convert these units. Let's say that work is equal to delta E is equal to F times D. And let's say delta E is equal to EF minus EI is equal to F times D. And let's say EF is 0, because it stops, right? If it's 0, sorry, if it stops, then the final energy is 0. Now, what kind of energy does it have when it hits the wall? When it hits the wall, before it begins to stop, it has kinetic energy. So we're going to say 0 minus 1/2 mvi squared equals F times D. Now we're going to rearrange this to solve for force. We get F is equal to negative 1/2 mv squared divided by 1/2 mvi squared divided by delta D. So the equation, or it becomes, when I sub in my numbers, negative 1/2 of 0.430 times VI. What's 130 in meters per second? 130 times 1,000 divided by 3,600 gives me 36.11. Divided by the displacement. How far does this ball move? During the time that it takes the ball to stop, it moves forward the amount that it's squished, 2.3 centimeters, or 0.023 meters. So let's figure this out now. Gives me a force here when I do this of negative 1. We want 3 digits, negative 1.22 times 10 to the 4 newtons. So what's the force of the wall on the ball? The ball is moving to the right. The wall pushes on the ball in order to slow it down to the left. That's why the force is negative, right? Now, what's the answer to the second part of this question? The force of the ball acting on the wall. Positive 1.22 times 10 to the 4, right? We don't have to figure that out, because we know that if object A applies a force on object B, the wall applies a force on the ball, then the ball applies an equal and opposite force on the wall. So of course it has to be equal in magnitude, opposite in direction.